Right now, look up. If you're inside, there's a ceiling a few feet over your head, held up by steel and math and a building code. Fine. Now picture standing inside a Gothic cathedral. The stone ceiling is 150 feet above you. It weighs thousands of tons, and it's been hanging there over people's heads for 800 years. Here's the part nobody tells you. The men who built that did not know how it worked. They had no physics, no concept of force or load or stress. The math that explains why that ceiling doesn't fall on you wasn't invented until 400 years after the building was finished. So how is it still up there? The honest answer is the uncomfortable one. They built it the way you'd learn to do anything dangerous with no instructions, by trying things, watching them collapse, and not doing that again. We like to imagine medieval master builders as secret geniuses who understood something we've forgotten. They weren't. They were brilliant, but they were working almost blind. There was no theory of why a wall held or why an arch stood. There was only a set of inherited rules. Do it in these proportions, and it tends not to fall down. Pass from one builder to the next, paid for in buildings that did fall down. Cathedral engineering wasn't calculated, it was accumulated. Centuries of failure, stacked up until the failures got rare. And the strangest part is the one we'll get to at the end. Those rules of thumb were secretly accidentally correct, for a reason no one alive at the time could possibly have known. Start with what they actually had in their heads because it wasn't equations. Around the year 1230, a Frenchman named Villard de Honnecourt filled a small sketchbook with drawings. About 33 pages of it survive today in a library in Paris. It's one of the only windows we have into how these people thought, and there is no math in it. None. No numbers being added, no forces being calculated. What's in there instead is geometry. How to draw a perfect shape with a compass and a straight edge. How to lay out a tower using a square inside a square. Little tricks for cutting a stone to the right angle without measuring it. Recipes. That's how the knowledge moved, as geometric procedures, guarded inside the masons' lodges like trade secrets. A master didn't tell an apprentice why a buttress needed to be a certain thickness. He told him the proportion. Make it this fraction of the height. Don't ask why. It works. And mostly it did work. But mostly is carrying a lot of weight in that sentence. Here's how you can tell they were guessing. In the 1390s, the city of Milan started building its cathedral, and they ran into a problem they could not solve by argument, because there was no science to settle it with. The question was simple. How tall and wide should the cross-section of the building be? Should the proportions follow a square or a triangle? This sounds like an aesthetic choice. It wasn't. The shape of that cross-section was the difference between a building that stood and a building that crushed itself. And the masters of Europe could not agree on the answer. They brought in a French expert named Jean Mignot to consult. He looked at the Italian builders' work and told them, flatly, that their structure was unsound. Their proportions were wrong. The Italians pushed back. They said their building was standing just fine. So what was the problem? And Mignot gave them the line that the whole history of this gets remembered by. Ars sine scientia nihil est. Art without science is nothing. Skill without understanding is worthless. The brutal irony is that he didn't have the science either. Nobody in that room did. This is one of the most documented engineering arguments of the entire Middle Ages. Historians have been writing about it since the 1940s, and what it actually records is a bunch of the best builders alive, standing inside a half-finished cathedral, fundamentally disagreeing about whether it was going to fall down. They were all working off rules of thumb. They just had different ones. A lot of what looks like genius in these buildings is actually a patch. Take the flying buttress, that elegant stone arm that reaches out from the side of the cathedral and props up the high wall. We treat it as the signature invention of Gothic architecture, a bold design choice. For some of the early ones, it almost certainly wasn't a choice. It was an emergency repair. At places like Notre Dame in Paris, the evidence suggests the builders pushed the walls higher than the stone could safely hold. The upper walls began to bow and crack under their own thrust, and then someone propped them up from outside before the whole thing peeled open. The fix worked so well it became the style. The thing we now copy on purpose started as someone catching a mistake in mid-collapse. That's the pattern over and over. Build too far. Watch it strain. Brace it. Survive. Tell the next builder, leave room for buttresses. Don't ask why. It works. And then there's the building that shows you exactly where trial and error runs out. Beauvais Cathedral in northern France. The builders there were in a height race, every cathedral trying to outsoar the last one, and Beauvais decided to win. They built the tallest stone vaults anyone had ever attempted, roughly 157 feet of open space overhead, higher than anyone had gone. Higher, it turned out, than they understood how to go. In 1284, 12 years after the choir was finished, part of those vaults came down. They rebuilt. They added more supports, more stone, more bracing, patching by instinct, because there was no calculation to tell them what had actually gone wrong. And it held for a while. Then in 1573, they put an enormous tower over the crossing, briefly the tallest structure in the world. It stood for a few years. Then it collapsed too. Beauvais was never finished. To this day, it's a magnificent fragment, a choir and a transept with no nave, a cathedral that bit off more than the method could chew. It's the clearest proof we have that nobody had the formula. When they pushed past the edge of accumulated experience, they had nothing to catch them. The building told them they'd gone too far the only way it could. It fell. Here's where it gets genuinely strange, and it took until the 20th century to find out. In the 1960s and 70s, a Princeton engineer named Robert Mark wanted to know how these structures actually carry their load. So he built small plastic models of cathedral cross-sections and put them under polarized light, a technique where stress inside the material shows up as bands of color. For the first time, you could literally see where the forces flowed through a Gothic wall. What he found was humbling in both directions. Some of the heavy, decorative-looking stonework that everyone assumed was ornament turned out to be doing critical structural work by accident. And some of the parts the builders clearly thought were holding the building up were barely carrying anything at all. They didn't know which of their own pieces mattered. They had built a machine that worked beautifully and couldn't have told you which gears were turning. So we're left with the real question. If they were guessing, if even their experts couldn't agree, if their masterpiece in Beauvais collapsed twice, how is it that so many of these buildings are still standing, perfectly 8 centuries later? The answer came from a modern engineer named Jacques Aymon, and it's the punchline to the whole story. For a building made of stacked stone, it turns out that strength barely matters. Stone is so strong in compression that it's almost never the thing that fails. What matters, almost the only thing that matters, is shape. Get the geometry right, get the proportions right, and the forces stay safely inside the stone, and the structure simply cannot fall. Get the geometry wrong, and no amount of strong material saves you. Which means the medieval builders, fumbling with their compasses and their inherited proportions and their lodge secrets, were obsessing over exactly the right thing. Geometry. They couldn't have told you why, but for masonry, geometry is the physics. They were playing the correct game without knowing the rules, and centuries of failure had quietly tuned their proportions toward the right answers. The math that proves all this? It showed up late. In 1675, the scientist Robert Hooke worked out that the ideal shape for an arch is the same shape a hanging chain makes, just flipped upside down. That single sentence is the key to the whole thing, and Hooke wrote it down 400 years after Notre Dame was already standing. The buildings came first. The explanation came centuries later, to describe something humans had already built by hand in the dark. So here's the full picture. They had no physics. They had geometry and memory. They passed down proportions like family recipes and refused to explain them. When they guessed right, the building stood for 1,000 years. When they guessed wrong, it came down on top of them, and they wrote that down too, in stone, in the shape of a cathedral they could never finish. Every soaring ceiling that survived is a guess that happened to be correct. Every one that fell was the experiment that taught the next builder where the edge was. The cathedrals we still walk into aren't monuments to people who understood. They're monuments to people who kept trying until the failures ran out. So next time you stand under one of those ceilings, 150 feet of stone with nothing visible holding it up. Don't think about faith and don't think about genius. Think about the chain, the flipped, frozen, perfect curve of a hanging chain that no one in that building had the math to describe, but that they found anyway, by hand, the hard way, one collapse at a time. They didn't know why it worked. They just knew it did. If you want to go deeper, Beauvais, the Milan debate, Heyman's work on why stone really stands, it's all linked in the description.